The HarrisCorner Detector gives a mathematical model approach for determining the best case in finding out the corners in a given image. So you can see here I do have the image. So this is a flat region where no change in all directions. That means if I move the mask to any direction, I won't have that much change in the intensity. And coming to here, there won't be any change along the edge direction. And coming to here, if I move the mask in any direction, I will find a significant change in any direction in its intensity level. Okay, so for this analyzing the HarrisCorner detector, let me take a function that is a window function w of x comma y, right? So if this window function is placed on some pixel where I will be getting the intensity as I of x comma y, and if I have shifted or translated to the location of u comma v, that means x and y, x is shifted by u units and y is shifted by v units. So that means this window is concentrating on some other pixel which is giving the intensity as I of x plus u comma y plus v. Now when I differentiate these two intensities, that means the new pixel intensity is this one and the old pixel intensity is this one. That means this is an intensity of the old pixel and this is the shifted intensity, that is intensity of the new pixel, and this is my window function, that is w of x comma y. So E of u comma v is nothing but change of intensity for the shift u comma v. So if it is a homogeneous region, that means all the pixels will be very uniform and they are giving or exhibiting the same intensity levels. That means can I say in that case it is a constant patch, the image is having the uniform distribution or the uniform gray level values in its pixels. So for the constant patch, can I write E is equal to, that means change of intensity is 0. And if it is find that the image is not having the constant patches, that means we do have different textures or intensities or colors or whatever it may be. So in that criteria, the distinctive patches criteria, E will be very larger. That means like with old pixel and new pixel difference only, it is making me a huge difference where I can find out that E will be, that means change of intensity for the shift of u comma will be very large. So the window function w of x comma y will be equal to 1 within the window and it will be 0 outside the window. Okay, so hence we want patches where E of u comma v is large. So our ultimate aim or goal is to find out the corner for a given input image here. Okay, so for which we take Taylor series into consideration. So why we have to take the Taylor series into the consideration is, so this expression, that is I of x plus u comma y plus v, can be expressed in Taylor series in this manner. That is, we know f of x plus u comma y plus v equal to f of x comma y plus u into fx of x comma y plus v into fy of x comma y. So this fx stands for the first partial derivative. That means it is a gradient along the x direction, and fy stands for gradient along the y direction, where u comma v are nothing but these are the spatial shifts in x direction as well as the y directions. Okay, and plus, so according to the Taylor series expansion for this unit, for this one we do have this one plus 1 by 2 factorial u square fxx of x comma y plus uv fxy x comma y plus v square fyy x comma y plus so on. So that means this is my second partial derivative and this will be my third partial derivative. In this manner it expands, right, for the higher order terms. For my best case, what I will be doing here is I would like to neglect the second and third and remaining all the higher order derivatives. So if I neglect all these terms, ultimately my f of x plus u comma y plus v equation will be resulting me in this manner. That means f of x comma y plus u into fx of x comma y plus v into fy of x comma y. Okay. So just substitute this expression in the given form here. So if I substitute there here, that means I of x plus u comma y plus v can be written as I of x comma y plus u ix plus v iy minus I of x comma y whole square. It is based on the above approximation. Okay. So the HarrisCorner detector derivative can be derived in this manner. So this is my first order approximation. Now can I cancel this term and this term, right? So that means it is in the form of a plus b whole square, that is a square plus 2ab plus b square. So this equation or this expression can be rewritten in the matrix representation in this manner. That is uv this manner, that is ix square, ix iy, ix iy, iy square and uv. So in this manner I can rewrite in the matrix format, right? Okay. So uv, and let me take the summation inside here. So finally I will be obtaining, that means this equation, this entire expression is converted into this manner, right? Okay. Now for the small shifts, that is u comma v, we can also take bilinear approximation into the consideration. That means E of u comma v equal to uv m u comma v, u of uv, because it is a transpose. That means it is uv and this will be uv, like this it happens. So that means this entire matrix I can represent by using capital M now. Okay, so where M is a 2 cross 2 matrix which is computed from the image derivatives itself only. Right. Okay. So w of x comma y, we know that it is a window function so it is computing a weighted sum, right? So sum over image region minus area, we are checking for corner. Okay, and this is gradient with respect to x times gradient with respect to y, ix iy. Okay, so in this manner we can rewrite the equation. And finally m equal to, so I want to take again the summation inside. So sigma summation ix summation ix iy, summation of ix iy and summation of iy into iy. Again I can rewrite this entire thing in this manner, right? It is simple mathematics only we are performing here. Okay, finally this thing can be expressed in this manner. How? By considering an axis aligned corner. So this is my corner, right? This is the axis aligned corner where so this means dominant gradient direction aligned with x or y axis. So if either of this lambda, that means either a lambda 1 or either a lambda 2, if it is found to be as 0, that means it is not a corner. So we have to look for a locations where lambda 1 and lambda 2 both are large for our best case analysis. Okay, now we do also have a corner response function. So what is this corner response function here? Corner response function is nothing but R, capital R, that is determinant of m minus alpha into trace of m whole square. So M is a matrix, that is lambda 1 and lambda 2. So determinant of M is AD minus BC. So A into D, lambda 1 into lambda 2 minus BC, that is 0. Minus alpha into trace of M is nothing but addition of the diagonal elements. So lambda 1 plus lambda 2 whole square. So alpha, it is a constant that is varying from 0.04 to 0.06. So this is the case when I am mainly focusing on corner case only, that is an axis aligned corner. Okay, so here what you can able to perceive that the distribution of the x and y derivatives is very different for all the three type of patches. So this is my homogeneous patch, right, where I can find a uniform intensity over everywhere in its pixels. That means both the gradients, which gradients here, lambda 1 and lambda 2 will be very less, right, or very small. That means lambda 1 and lambda 2 I can also call them as the eigen values. So both the gradients along the x as well as along the y are very small. So that is why I have represented this with a circle. And coming to this one, it is a linear edge. So if I move my mask along the edge, so what happens? My gradient will be high only along one direction only. That means if it is a vertical, means vertical gradient will be high. Horizontal means horizontal gradient will be high. Okay, so in this case, gradient along the x direction increases and y direction will be decreasing. That means lambda 1 is higher, lambda 2 is smaller in this case. But coming to here, where a corner I have found, right, because this is the mask, right, so this mask I have found or I placed at a corner. Okay, so where I can have the gradient along the x direction as well as the y direction are higher. That means lambda 1, the eigenvalue lambda 1 and eigenvalue lambda 2 both are higher for a corner case here. So what I will be doing here, I just fit an ellipse so such that in order to plot the derivatives, that is ix or iy, just I have taken an ellipse with red color in ink. So this is in x direction and this will be in my y direction. So this is so I can also represent like how to find a corner with these eigenvalues by using the upcoming figure. So that means classification of image points using the eigenvalues of m. So what is actually this m is? M is nothing but this is the one that has been derived from the Taylor series expansion expression. Okay, so m is this one. Okay, so classification of image points using eigenvalues of m. So this is my lambda 1 and this is my lambda 2. Okay, so if lambda 1 and lambda 2 are small, that means can I say E is almost constant or equal to 0 in all the directions? So that means it is indicating me that it is a flat region or a homogeneous region where lambda 1 and lambda 2 are small and E is almost constant in all the directions. And coming to here, for the horizontal edge, lambda 1 is greater than lambda 2. Okay, so this is my vertical edge, right? So let it be a horizontal or vertical edge. So for the representation I have taken in this manner. So for a vertical edge, lambda 1 is greater than lambda 2, and for my horizontal edge, lambda 2 is greater than lambda 1. And for the corner case, the M matrix where the lambda 1 and lambda 2 should be very, very larger. That means E increases in all the direction. What is E here? It is the intensity change for the shift of u comma v for a given mask. Okay, then the corner response measure. So that's the same thing. That means the classification of image points also can be done. Instead of eigenvalues, I can also use this R. So that is corner response measure. So coming to the corner response measure, what is the formula for the corner response measure? R is nothing but determinant of m minus alpha trace of m whole square. So similarly, that means lambda 1, so that means when r is less than 0, it is considered as an edge. When r is greater than 0, it is considered as a corner. When r is very, very small, it is considered as a flat region. So this is about the corner response, how by the classification of image points can be done by using this capital R into consideration, right? Okay, so this is the given input image. I need to find out the corners. So compute corner response and find points with larger corner response, because I need to find out what corners, right? So it should be greater than some threshold, and after that one I will be resultant with this one. So I need to take only the points of local maxima of corner response here. Okay, so what are the properties then? Okay, of course these are the corner points finally. And what are the properties so of this corner response? It will be rotation invariance. Like you can see, if the ellipse rotates like this in clockwise direction, its shape is remaining same, right? Okay, and and the corner response, that means here this corner response, it is invariant even though the ellipse is rotating. So I can say that the corner locations are to be invariant to either a photometric transformation or affine transformations also, right? So the same thing in a summary point we can visualize in this manner. I have given an input image in this manner. So the image derivatives, that is derivative along the x direction, and this is my derivative along the y direction, right? So it is the first partial derivative and it is the second partial derivative with respect to x and with respect to y. So ixx and here square of derivative ix square, and this is iy square, and this is ix iy. So partial derivative of y with respect to partial derivative of x here. So using Gaussian filter I have done the convolution. So this is my resultant image where smoothness of image increases and a little blurring also increases here, and compute second movement matrix M and corner response R. So this M is nothing but it is a second movement matrix M, where M equal to, so convolution of this matrix with a Gaussian filter, I will be getting some resultant in the form of g of ix square, g of iy square, and g of ix iy. So the corner response is nothing but this is the old formula, that is determinant of M minus alpha into trace of M of the matrix. Okay, so finally I will be obtaining my corners in this manner. So these are nothing but the corner points for the given input image or the interest points. Okay, so there is one more detector that is also have to be taken into the consideration, that is a Hessian detector. So where we have to search for image locations which have strong changes in the gradient along both the orthogonal, that means along both the x as well as the y directions, that means along the horizontal as well as the vertical directions. Of course this is this matrix you are very much familiar. So determinant of A is nothing but lambda 1 lambda 2, and trace of M is nothing but lambda 1 plus lambda 2. Okay, so determinant of this Hessian matrix, so ixx of x, iyy of x minus ixy square of x. So this ixs is nothing but it is the second partial derivative with respect to x or in x direction, and it is second partial derivative in y direction, and this ixy is a mixed partial derivative in x and y direction. So the purpose of this Hessian detector is where one can eliminate some false corner points if still exist by any of the corner detection technique. So this is about a Hessian corner detector. Okay, the same thing mathematically is being represented in this slide. Okay, so here it is ix and iy, it is ixy. So the difference you have to notice here, it is the mixed partial derivative in x and y direction, ixy is. Okay, so it is partial derivative of x into partial derivative of y. Okay, so this is about the Harris and Hessian corner detectors. And thank you. Have a nice day.